Okay, so we are going to practice calculating truss forces. And so while you are doing this, you want to make sure you have this step-by-step truss instructions handy, as well as a scientific calculator. So a scientific calculator, you need to make sure you have trigonometric functions, so sine, cosine, and tan. If you don't have a calculator, you can go online and use desmos.com/scientific, which is what I use. So let's look at our first example, and we want to make sure we walk through these steps. So the very first thing that we are going to do is we are going to draw the truss. We're going to place dots at each of the joints and label them, and we're going to identify the reaction forces at the roller and pin support, and find any necessary unknown angles within the truss if they are not given. So let's do those steps first. So let's draw our truss. So let's say here is example 1, and it's going to look something like this, with a pin support over here and a roller support over here. Let's label the joints A, B, D, and C. There's going to be an external force on joint D. Let's say it's 500 pounds. We'll just call it F1. And let's put some dimensions on this truss. This is usually given to you. So let's say from A to D, this is 3 feet. The distance from B to D is 4 feet. And from D to C is 7 feet. Well, to do any truss calculations, you need at least one angle in each of the right triangles you see. So that would mean we need this angle here and this angle here. So let's find theta A, angle of A. So that's the step we're on, is find the angles. So to find theta A, we can see that relative to angle A, we have the adjacent side, which is 3 feet, and we have the opposite side, which is 4 feet. So we're going to be using tan. So tan of theta A is opposite over adjacent, which means tan of theta A, now we plug in our values, is 4 feet over 3 feet. And to find theta, we need to take inverse tan. So theta A is inverse tan of 4 over 3. And when you plug that into your calculator, make sure you use inverse trig functions. I recommend doing this at the same time that I do it. And use your scientific calculator, you get 53.1 degrees. Okay, so let's replace that theta A with the correct value. So this is 53.1 degrees. Let's do the same thing, but this time for theta C. All right, well, for theta C, 4 feet is still our opposite side, and 7 feet is our adjacent. So we're going to use tan again. So tangent theta C is opposite over adjacent. So theta C is going to be inverse tan of opposite over adjacent. Let's plug in our actual values. We get 4 over 7. And if you plug this into your scientific calculator, you get, let's see, 29.7 degrees. Okay. All right, let's go back to our step-by-step instructions sheet and see what's next. All right, well, let's see what we've covered already. We did this, draw the truss, we placed dots at each of the joints. We found unknown angles, but we didn't identify any of the reaction forces at the roller and pin. So let's do that. Okay, so our reaction forces, we know there are two at a pin support. We know there is an up reaction force and a horizontal reaction force. And on a roller, there's only a vertical reaction force. So we call this reaction force. Since it's at joint A, we're going to call it RA. And since it's up, it's going to be, or in the vertical, it's going to be RAY. This one is also RA, but since it's horizontal, it's RAX. This one is vertical, so it's RCY. Okay, we always assume that the reaction forces are in the positive direction. So for the up component, or for the vertical component, it's always up. For the horizontal, it's always to the right. Okay, let's see what's next. Okay, so we are now on step 2, which is calculating the reaction forces at the roller and pin connections. How we're going to do that is summing up our moments to find one of the reaction forces. We want to make sure that we always choose our pin location as our pivot. It's really important because that has two reaction forces, and that way we can eliminate two of them right off the bat because they are no distance away from the pivot. Okay, so let's do this. We can go ahead and talk about these next two steps also, which is summing up the forces in the x direction and summing up the forces in the y to find the unknown reaction forces. Okay, so we want to sum up our moments. And since, like I said, we set point A as our pivot, there is no moment due to RAY or RAX. There is going to be a moment at point D because there is a force applied at point D, an external force, and there's going to be a moment at C because there's a reaction force, and it is a distance away from point A. Well, now we need to identify which is positive and which is negative. So we need to make sure we look at our coordinate system, and we know that counterclockwise is positive. Counterclockwise is positive. So if we apply a force at point D, that's actually going to cause the truss to rotate clockwise. So that is going to be a negative moment. So add a negative sign in front of MD. And if we apply a force at point C, that moment is going to be counterclockwise. So it is positive. All right, now we can go ahead and actually use the equation for a moment, which is just force times distance. And we're looking here at the force applied at point D and the distance from D to the pivot point, which is point A, plus the force at point C times the distance from C to A. And don't forget that our force is always perpendicular to our distance. So since our two forces we're talking about here are vertical, we're going to be dealing with horizontal distances. All right, let's plug in anything we know. So we know the force at D is 500, so let's plug that in. 500 pounds times the distance, which is 3 feet, plus the force at C. Well, we don't know that, but we call it RCY based off of our picture. And we do know the distance is 7 plus 3, so 10 feet to point A. And let's set that equal to 0, then let's solve. So we get here, we get negative 1,500 foot-pounds plus 10 feet times RCY. Well, we want to solve for RCY. It's like our unknown. It's our X. So we need to add 1,500 to both sides. Foot-pounds is just the unit, so we just keep it with the number. Well, negative 1,500 plus 1,500 is just 0, so that drops out. So we're left with 10 feet times RCY equals 1,500 foot-pounds. Well, we want RCY, so we need to divide 10 feet on both sides. On the left-hand side, 10 feet divided by 10 feet is just 1, so we're left with RCY equals 1,500 foot-pounds over 10 feet. Well, if we look at our units, we could see feet over feet is just 1. So we're left with 1,500 over 10. Well, that's 150. And our units are pounds, which is exactly what we want. So as soon as we find any forces, we want to make sure that we box them because they're going to be useful to us. And since 150 came out positive, that means it's pointing up. So we predicted it to be pointing up, so that's the correct direction. All right, now we're going to follow in those next steps, which is sum of the forces in X and sum of the forces in Y must equal 0. Let's deal with X first. So looking back at our picture, we need to look at any of the forces that are in the horizontal. Well, the only force is RAX. Since there is no other, that means RAX must equal 0 pounds. Let's box it because we're going to need it later. And now we want to sum up our forces in the Y. So we need to write all of our forces that are in the Y direction or the vertical, which if we look at our picture, it's RAY, 500, and RCY, which equals 0. Now, don't forget to make anything negative that's pointing down. So in this case, the 500 is pointing down, so it's negative. And the next step, let's go ahead and fill in anything that we have already found. Well, in the previous step, we found RCY. So plus a negative 500, same thing as minus 500, plus 150 equals 0. Well, if we add negative 500 plus 150, that's really negative 350. So we have RAY minus 350 equals 0. And to get RAY by itself, we add 350 on both sides. So we get RAY equals positive 350. Okay, there's another force, so we want to box it. All right, we have found all the reaction forces, and we know the external force is 500. So let's go back to our step-by-step instructions and see what's next. So we are moving, right along to step step 3, sorry. Okay, so step 3 is to draw a free body diagram for the entire truss structure that you are analyzing. We want to make sure we include all external forces, reaction forces, and internal forces, which is the new part. So internal forces are the forces that exist within the members. Okay, let's do that. So I like to basically just draw all the joints first. So our joints relative to each other, we had joint A here, we had joint B up here, D right below point B, and joint C was off over here. So we can kind of see that it is in the formation of our actual original picture. Now let's draw our reaction forces first. Okay, on joint A we had RAY, and we knew that it was up, so we're going to point it up. And at joint C we had RCY. And we did have RAX, but since we calculated it to be 0, we're not actually going to draw it on our free body diagram because the force is 0, we don't need to draw it. So let's draw our external force. So at joint D we had F1 down. Okay, and then we need to draw all the internal forces. So between joints A and B, there's a member. So we're going to have a force pointing in towards the joints. And since it's between points A and B, we're going to label it FAB. Same thing with this one, FAB. It doesn't really matter whether you call it FAB or FBA. Okay, and so then between B and D, always point the arrows toward each other. We always assume positive. So FBD. And then between joints A and D, we have FAD. 2 more. We have FDC and FDC. And between joints B and C, FBC and FBC. Okay, so let's go back to our step-by-step instructions and see what's next. So we did our free body diagram. Let's make sure we create a summary box next. So the summary box is where we can document all of our known forces, external, reaction, and internal. All internal forces should point toward the inside of the truss. We assume they are all in tension to begin with. Unless they point outside of the truss after we've calculated, then we make them compression forces. So let's make a summary box. So somewhere on your sheet, I always like to do it at the upper right-hand corner. And we're just going to list all of our forces. So I always start with the external forces. So F1 was our only external force, and it was 500 pounds. Since it was pointed down, it was negative. And then I go to the reaction forces. We had RAX, RAY. RAX was 0. RAY was positive 350. And RCY was positive 150. Then we list all the internal forces, which are the forces that we have to solve for next. So go back to your free body diagram. We have FAB, FBD. So I'm going to start with joint A. So we had FAB. Also on joint A is FAD. And then joint B. Since we already listed FAB, we don't need to list it again. We have FBD and FBC. Oops, said FBD, but I wrote BC. There we go. And then we have to identify any other internal forces, which it looks like what's left at joint D, we have FDC. So let's add that one. A good rule of thumb to help you remember is that however many members you have is how many internal forces you're going to have. So we have member AB, BD, AD, DC, and BC, which is 5. So we should have 1, 2, 3, 4, 5 internal forces. Great. Okay, so let's go back to our step-by-step instructions and see what's next. Okay, so we need to choose a joint to analyze. Step A, part A, says start with the joint that has the fewest unknown forces as well as the most known forces. Usually this is the joint with the least amount of internal forces at angles. I always start with the pin, our pin support, or our pivot, which is always our pivot. Oops. So this is always the pivot. Then we draw a free body diagram of that particular joint. Again, we break up the diagonal forces into their X and Y components. So let's do that. Okay, so since we're going to start with our pin support, we have joint A, so we're going to write joint A. And then we're going to draw a free body diagram, but this time we're going to break up the diagonal forces into their X and Y components. So here is FAD, which is not diagonal, it's horizontal, so it's already good to go. RAY is vertical, so nothing to break up there. I am going to draw the diagonal force a different color so we can deal with it. So this diagonal force is FAB. And if we remember back to our original picture, we solved for this angle, which was 53.1 degrees. So using your prior knowledge, we can break up FAB into its horizontal, so its X component, and we'll call this FABX, and its vertical, FABY. Since we don't want to introduce any new forces, we want to get FABY and FABX in terms of the angle that's given as well as FAB. So how we do that is we use our trig functions. Since FABY is the opposite side and we want to always use FAB, the hypotenuse, we're going to be using sine. So sine of 53.1 degrees is opposite of our hypotenuse, so FABY over FAB. Well, when we solve for FABY, we want to multiply FAB on both sides. And we're left with FABY is equal to FAB times the sine of the angle. So at this point, you can go ahead and jump right to the conclusion that the y component, or the opposite component of the angle will always be sine, and the adjacent component will always be cosine. So FABX is going to be the same thing, but cosine. You don't have to go through the process of showing me this step every time. Like I said, opposite is always going to be sine, adjacent is always going to be a cosine. Okay, so let's go back to our step-by-step instructions, see what's next. All right, the next step is to use sum of the forces in the x equals 0 and sum of the forces in the y equals 0 to solve for the internal members. Okay, after we're done with that, we are going to write the magnitude, which is just the size or the amount of the internal force, in our summary box, and we're going to state whether it's in tension or compression. Okay. So let's do that. Let's start in the x direction or y. It really doesn't matter. In this case, since I already know RAY, I'm going to start in the y direction. So sum of the forces in y must equal 0. So we have RAY is up, and let's replace this FAB with its components instead. So we had FABX and we had FABY. Oops. Sorry about that. So we have FABY. Okay, so RAY plus FABY must equal 0. Let's plug in anything we know. We know that RAY was, go back to your summary box and look, 350. So let's plug in 350 here, plus FABY, well, we're using this equation right here, which is FAB sine 53.1 degrees, and set it equal to 0. Our unknown is FAB, so let's solve. Let's subtract 350 on both sides. And then we're going to divide by sine 53.1 on both sides. So this is where you're going to need a scientific calculator. So we have FAB equals negative 350 divided by sine of 53.1. When you solve for this, you should get a negative 437.7 pounds. Since this is another force, we need to box our final answer and then put it in our summary box. Okay, but before we put it in our summary box, let's look at what the negative means. So we predicted FABY and FABX to be positive, but what's actually happening here is FAB comes out as negative, which means in reality, instead of FAB pointing this way like we predicted it to be, a tension force, it's actually pointing the opposite. And this makes sense because if we look at, let's get rid of the ones that are not in the right direction. If we look at this free body diagram now, we can see that it is in equilibrium. So I always think of equilibrium like a tug of war. If there's a person on RAY and a person at FAD and a person at FAB pulling, it's a tug of war that is equal. No one wins. It's a tiebreaker. So anytime you figure out that the force is actually in the opposite direction, so in this case it is, this is not a tension force, but it's a compression force, we need to go back to our original free body diagram, which is right here, and change the direction. So instead of FAB pointing this direction, it's actually pointing this direction. Same thing at joint B, we need to change it. So here's FAB, and then get rid of the other one, the one that was actually wrong. Because at the end, you want your overall free body diagram of the whole truss to look like it's in equilibrium. All right, so let's go back and put that negative 437.7 into our summary sheet. So we're going to drop the negative, and just make it a compression force after. So put the letter C, because the negative only told us the direction. So we care about whether they're compression or tension forces. Okay, so we're almost done with joint A. There is still one more force at joint A that we have yet to solve for, which is FAD, and it's in the X direction. So let's do the exact same thing we just did with the Y, but in the X. So in the X direction, we have FAD plus our FABX equals 0. But instead of FABX, we always write it as with the sines or cosines. FAB, in this case, it's cosine 53.1 equals 0. Okay, so since FABX is actually a component of FAB and we discovered that it's pointing negative, we need to make our FABX negative. So this is a negative here. Now when we solve for FAD, we get FAD. If we add FAB cos 53.1 to both sides, we get FAB, oops, FAB cos 53.1. So that's what FAD is. Well, we already found FAB. It was 437.7 times cosine 53.1 degrees. So plug that in your calculator and we should have FAD. All right, when we plug it into our scientific calculator, we get 262.8 pounds. Well, in our free body diagram, we predicted it to be pointing to the right, which means it was positive. Well, after we calculated it, it came out positive, which means our prediction of it being a tension force was correct. So we don't change its direction. It is correct. So let's add that to our summary box. And write the letter T for tension after. Okay, so let's move right along here. After we deal with one joint, we have to deal with another, but let's make sure we're following these step-by-step instructions. Okay, so we are at step 2, which is to repeat until we have solved for all internal member forces. All right, well, the next step is to pick which joint we want to deal with next. Well, we have to choose the joint that's easiest to solve. So since we already solved joint A, and I always think that the second choice is always going to be the one with the least number of diagonal forces. Well, if we look at joint B, we can see FAB is diagonal and FBC is diagonal. If we look at joint C, we see that FBC is diagonal. And if we look at joint D, there's no diagonal forces. So our next easiest one would be joint D. All right, so let's do the exact same steps we just did. We write joint D. We draw a free body diagram for it. So the same free body diagram you drew before. And it had an external force pointing down, which we called it F1, and it was 500. Okay, so we get to skip this green step that we did earlier because there aren't any diagonal forces, and we get to jump right to summing up the forces in the X and Y. Well, I'm going to do the Y force again. I'm going to do that one first because we know the 500, which is in the vertical. So sum up our forces in Y must equal 0. So we have force BD plus 500 equals 0. And since 500 was down, it was negative. Well, if we solve for FBD, we add 500 to both sides since it was negative, and we get FBD equals 500 pounds. And since it's positive, that means it must be pointing up, which it already is, so the force is in tension. So let's add that to our summary box. So this is 500 pounds in tension. Okay, let's go back to our joint D and do the same thing for the X. We have some of our forces in X equals 0. We have two forces in the X direction, or the horizontal, which are FAD and FDC. Equals 0. Well, we already solved for FAD earlier. It was, go back to our summary box, 262.8. And let's write that in. But this case, our FAD is pointing to the left, so we do need to make it negative. Negative 262.8. So when we solve for FDC, we add 262.8 to both sides. We're left with FDC all by itself, which is great. We get 262.8 pounds. So we solve for another internal force, so we box it, and then we have to go back to our free body diagram and state whether it's in tension or compression. Well, we predicted it to be positive to begin with, and it is a positive number, so that must mean it's tension. So let's add that to our summary box, 262.8. Okay, we're only left with one internal force left, which is FBC. So that means we have to deal with joint B or joint C next. So let's go back to our free body diagram and look at what's the easiest. Joint B or joint C? Well, if we look at joint B, like we did earlier, it has two diagonals, and joint C has only one. So obviously C is going to be the easier one to deal with. So let's draw joint C. Okay, here was our joint C. It had a reaction force pointing up, RCY, and it had FCD pointing toward the inside of the truss, which was the correct direction that we found earlier. And then we have a diagonal force, which is FBC. And like we did with joint A, we have to actually break up FBC into its components. So that's what we're going to do next. This angle that we calculated earlier, if you can't remember it, go back up to the top. It was 29.7, okay? So this is 29.7 degrees. So let's draw our force vector right here, FBC, and break it up into its components. So we have a left component, so FBCX, and we have an up component, so FBCY. Like I said earlier, you don't have to show your trig calculation anymore. You can just jump right to the conclusion that opposite is sine. So if we're finding FBCY, it's the force times the sine of the angle. And the adjacent is going to be the cosine. And then we're going to sum up our forces. Well, I'm going to go ahead and replace FBC with its components. So we have, actually let's do it in green. So we're predicting it to be to the left, FBCX, oops. And then we predicted FBCY to be up, which right now we could see is not going to work out for a free body diagram in equilibrium. It doesn't make sense. It's not a tiebreaker. So really FBCY is more than likely going to point down, and FBCX more than likely is going to point to the right. But we're going to let the calculation prove to us that that's that direction. So let's sum up our forces in the it really doesn't matter, X or Y, because we know RCY and we know FCD, so whichever one you want. So let's sum up our forces in the Y direction, equals 0. We have RCY plus FBCY equals 0. Well, we need to substitute our FBCY into our equation, which is RCY plus FBC sine 29.7. Okay, well, RCY, I can't remember it, so I need to go back up to where we solve for it, or our summary box. There it is. RCY was 150. So now we can plug this in. This is positive 150 since it's pointing up. And let's solve for FBC. So we subtract 150 on both sides, subtract 150 on both sides. We get FBC times sine 29.7 degrees equals negative 150. So we know it's going to be a negative number, which means our prediction, this dotted vertical, is going to be correct. So let's finish out the problem. Let's solve for FBC. Let's divide sine 29.7 on both sides. Okay, we get FBC all by itself. And plugging it into a scientific calculator, we get FBC to be about 302.5. Negative. Which, remember, the negative, we only want to write the magnitude, so the amount, not the direction. So negative doesn't really matter. But we care about the actual direction here. So instead of what we predicted, we know that we predicted FBC to be up this way. It's actually this way. So we need to get rid of all the other vectors that we have drawn that are incorrect. Well, don't get rid of too much like I just did. So FBC is pointing this way, which makes sense. Now our free body diagram right here looks like it's in equilibrium. So that must mean since we changed the direction, it's a compression force, not a tension. We have to go back to our free body diagram, our original, and change the direction of both of those FBCs. So instead of up and to the left, it's down and to the right. And same thing with the other FBC. Instead of down and to the right, it's up and to the left. And go ahead and erase the other incorrect ones. And now we can look at each of our joints and see that they are all in equilibrium. Okay, don't forget to plug in that last force we just solved for into our summary box, which was 302.5, and it was a compression. Okay, we can't forget that our overall objective was to predict which of the members is going to break first if we are to apply a force at joint D. Well, how we look at that and how we predict it is based off of how much each of these forces are. FAB was 437.7, FAD was 262.8, FBD was 500, FBC was 302.5, and FDC is 262.8. Whichever of those internal forces is the largest is the one most likely to break first. So that would be, in this case, FBD would break first. And that's this member right here. Okay.